My name is Al-Khalili, and I'm Emeritus Professor of Physics at the University of Surrey. My book is called On Time, the Physics That Makes the Universe Tick.
The next wave of quantum technology.
Here we are, a quarter of the way through the 21st century, and celebrating the most, in my view, powerful and successful scientific theory we have ever come up with, quantum mechanics. Quantum mechanics was developed in the early decades of the 20th century and describes the way atoms and the particles that make up atoms, the tiniest building blocks of matter, how they behave. And they behave in a way very different from the way our everyday world behaves. Quantum mechanics as opposed to Newton's mechanics and Newton's laws of motion. So in the quantum world, things are fuzzy, they're probabilistic. An electron can be in more than one state at the same time. Particles can move in multiple directions at the same time. They behave like spread out waves. They can quantum tunnel through energy barriers like a ghost passing through a solid wall. Things that we'd never see in our everyday world. And yet that reality down at the quantum realm is our true reality. Everything is built from that. Our whole universe ultimately behaves in a quantum way. Now, the early discoveries of quantum mechanics led throughout the 20th century to all sorts of technologies, what we now call the first quantum revolution. So the laser, the transistor, LEDs, the integrated circuits, the microchip, the computer, GPS, smartphones, the internet, almost all of our modern technology that we use today that relies on electronics is thanks to developing quantum mechanics. Today, we're on the threshold of a second quantum revolution, a revolution in technology based on even more counterintuitive ideas of quantum mechanics, things like quantum entanglement and quantum superposition. So many people may have heard of quantum superposition in the context of the so-called two-slit experiment, where you send particles through a screen with two slits, and it forms an interference pattern at the back. Somehow the particle goes through both slits simultaneously and behaves like a wave. So superposition is strange. Quantum entanglement is even stranger. This is the notion that even Einstein famously didn't like when he first encountered it, that two separated particles can somehow be instantaneously in communication with each other. Their fates are intertwined because they have to be described by the same single quantum state, however far apart they are. Well, we're now using superposition and entanglement to develop whole new technologies. Some are coming. They will be with us in maybe in a decade or two, like the quantum computer. Others we already have. So we are now developing instruments that carry out what's called quantum sensing. We have even developed this way of sensing very weak magnetic fields. You wear a helmet, like a cycling helmet, on your head, and thanks to quantum entanglement, we can measure the firing of single neurons, so essentially reading people's brain waves. One other technology that's being developed at the moment is quantum communication. Now, we know the way the internet is connected up through optical fibers. We send lasers through these fibers, and the coherent light that links different nodes around the world, linking computers. What if we could use the notion of quantum entanglement? So photons that could be sent along optical fibers can nevertheless be quantum entangled with other photons very far away from them. You could use quantum information to communicate and link the world. What if we had quantum computers that are linked via quantum information? Now we would have something called the quantum internet. Quantum imaging is something that's developing. There's this wonderful idea, what's called the entanglement camera, whereby you have two particles of light, two photons. One is visible in the visible range of the spectrum, and one is an infrared photon. These two photons are quantum entangled. So what happens to one influences the behavior of the other. The infrared light is very good at imaging, particularly imaging biological tissue, whereas visible light is much better to create images in cameras, so much sharper images. So you send the infrared light to probe biological tissue, for example, looking for cancer tumors, and then the visible light will create an image of what the infrared light sees, even though the visible light has never been near the physical object itself. It's magically transferring this information via quantum entanglement. So these are devices that are already being built and already being used to help in medical imaging, for example. The quantum computer, of course, is the poster child of the second quantum revolution. Quantum computers famously operate very differently from classical computers. They don't rely on bits of information that are 0 or 1, but rely on quantum bits of information, qubits, that are both 0 and 1 at the same time. And this gives us scope for exponentially increasing the power of computations. They're the ultimate in parallel processing. A quantum computer, when we have it, will one day be able to solve problems that the most powerful supercomputers we have today would take billions of years to solve. Quantum computers, we hope, will be able to help us in new drug discoveries, in better climate models, in financial transactions, in studying the behavior of quantum systems in research labs, in physics and chemistry. They won't be able to do everything, but they will have specialized applications that are going to change the world. There are, of course, many challenges still ahead of us. For example, in a quantum computer, it's not just about having a qubit that can be off and on at the same time. You have to have many qubits quantum entangled together. And together they form the quantum processor that can run quantum algorithms, that can carry out computations down in the quantum realm. But of course, linking these qubits together via entanglement is subject to disturbance from outside, what's called decoherence. The idea that the quantum effects are very delicate and ephemeral, and they will dissipate very quickly, like putting a hot cup of coffee in the freezer. It won't stay hot. Well, in the quantum world, decoherence happens very, very fast. And one of the biggest challenges is, how do you maintain the quantumness of your computer for long enough for it to do the computations? This is related to what's called quantum error correction. You have to build in a certain redundancy. So if you need 100 qubits to carry out a computation, you probably need 1,000 or 1,000,000 just to make sure that collectively you get an answer, even though some of them are useless because of decoherence. Another problem is of course, what do you build a quantum computer with? There are multiple options for what's called the substrate would be. What is the hardware that the quantum computer will be? There are lots of candidates, and we don't know which is the best one. Maybe they will be using what's called superconducting circuits, electrical circuits that are at temperatures near absolute zero, such that this quantum effect called superconductivity suddenly appears, where you have electrical currents flowing through wires with zero resistance. Now you can start to use these superconducting wires to carry out quantum computations. They behave like qubits. You could build a quantum computer out of light, out of photons of light traveling through fibers. You can build it out of clouds of atoms that are suspended in a magnetic field and held in place and cooled down to near absolute zero by laser beams. And those atoms then, they can be pumped with energy with other lasers such that you put them into a quantum superposition of being in two energy states at the same time. So now you have clouds of atoms that form your quantum computer. You can have strings of atoms that are missing or have extra electrons, so they're ions, they're electrically charged. They form the qubits. The fact they have electric charge means you can hold them in place using electric and magnetic fields. So there are lots of options. We don't know which is going to be the best one. And then even when you build a quantum computer, what do you run on it? What are the quantum algorithms? What's the code that you write that's going to carry out a quantum computation? We have a few already. what's called Grover's algorithm, Shor's algorithm, named after the people who developed these software algorithms. We need more, and there's still work being developed as to when you have the hardware, what is the software that's going to do it justice. Some will argue that a quantum computer will be with us in 2 or 3 years' time, if you believe the hype. I think realistically, we're talking about a decade or two from now. Are we here, as it were, playing God in developing technologies that are so outlandish, so far beyond anything that might occur naturally, that we don't even know what the implications or ramifications would be? I don't think so. I think we've always developed technologies that are based on our understanding of the workings of the universe, on the laws of physics. I think this is no different. More to the point, some of these very strange implications of the quantum realm, these new technologies that we're thinking of building, may, in some sense, already exist. Life may have hit upon the tricks of the quantum world and has used it to its advantage. So there's a new area of science called quantum biology, which uses the laws of physics to try and apply the laws of physics inside living cells, asking the question, has life, over the billions of years that it's been around, figured out how to use the tricks of the quantum world to give it an advantage? It's not magic. If quantum mechanics isn't magic, if life thinks that following a quantum process gives it an advantage, it will use that quantum process. Whether it's tunneling of particles from A to B is a more efficient way of transferring them than to move a classical particle, it will use quantum tunneling. Some have argued that maybe our brains are quantum computers. I think that's going much too far. We don't understand the nature of consciousness as it is. Let's not bring in quantum mechanics there. But there may be processes in nature, such as photosynthesis, where there's the hint, the possibility that some sort of quantum mechanism is taking place, quantum superposition. Maybe in our challenge to stave off decoherence to build a quantum computer that can carry out a computation long enough before that entanglement disappears and decoheres, maybe life has evolved the tricks inside the warm, hot, messy, noisy living cell where thousands of chemical reactions are taking place. Nevertheless, it's been able to maintain quantum coherence long enough to have some biological function inside living cells and keep decoherence at bay for long enough for that to happen. That's something that I find very interesting. Has life figured out the tricks that we're trying to solve now to build a quantum computer? If so, life's had long enough to be able to figure it out. We can shortcut it. We can just copy what life has done. We talked today about the revolution in artificial intelligence. Well, the second quantum revolution, I believe, will be just as important and just as impactful. Never mind when quantum technologies merge with artificial intelligence, then wow, who knows what will come.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.